cloud-native storage. So the first problem when you think about this is that no application, there's no such thing as an application that doesn't need to store state somewhere, right? Every application needs to store state, and there's no such thing as a stateless architecture. And why is this, right? We talked a little bit in the keynote about stateful applications being the next natural evolution. But why is that? So the first thing is, if you've been going to KubeCon for a while, you'll know the distinction between cattle and pets. So pets are these carefully curated servers, and cattle are like a more homogeneous set of resources that are automatically managed. And the same thing applies to storage environments. A lot of storage systems are traditionally implemented as these point-in-time solutions. And what we want to do is we want to take all of the advantages that we've gained in our containers and in our orchestrated environments to take advantage of that with our storage environments. So we don't want pets. We want to have these. We want to have more automated cloud-native storage. And why is that important? Well, the other important thing is you've made all of this effort to make your containers portable. You've made all of this effort to allow your containers to be moved from one node to another, from one cluster to another. And we really need to find ways now to make sure that the data can follow the application, so your stateful applications can continue to consume storage as they move in an orchestrated environment. And finally, and you know, this is also one of the drivers as to why Kubernetes is becoming such a huge success story in enterprises, is humans are fallible. So you also want to be able to compose your environments such that the Kubernetes or the orchestrator can handle the automation for you. The vast majority of outages are inevitably down to, you know, change management gone wrong or operator error. So taking that human error out of the equation is a huge win in stateful applications and cloud-native storage too. So we sat down and we talked a little bit about what's important for cloud-native storage and what are the things that you should be considering when looking at cloud-native storage. And we put together these kind of 8 principles that sort of serve as an easy way to compare storage systems and compare how you're implementing storage in your environments. So one of the big differences in cloud-native storage, and the first thing that changes completely, is that we're kind of moving from a legacy environment where storage is presented to an individual server or an individual operating system or a VM. And instead, we're now presenting and consuming storage through applications. So in very simple terms, this cloud-native storage needs to be more application-centric. So it should be consumed by the applications and not by the operating systems. We talked, again, we've already mentioned several times about the portability that containers gives you and the ability to abstract your infrastructure with Kubernetes. So in many ways, if you want storage that fits in with that sort of environment, you also want cloud-native storage to be able to run anywhere and scale and upgrade with whatever platform that you've abstracted with Kubernetes. Because we're deploying cloud-native storage with orchestrators like Kubernetes, you also want to be able to declare and compose your storage. So in very similar ways to the way we can declare the network ports that an application needs, the CPU and memory requirements, you also want to be able to define what your storage requirements are and allow Kubernetes to manage that storage environment and dynamically provision storage and all the resources from a storage point of view too. Now, in order for the storage to be declarative, it kind of implies that it needs to be API driven. So it needs to have a good management interface that can connect in with the orchestrator, and it needs to be. And the orchestrator needs to provision, move, and manage that storage through the life cycle of that application. Now, we talk about the portability and we talk about the infrastructure abstraction, and I'm kind of repeating these over and over. But what this means is that these applications are going to be moving into lots of different environments. So there's no guarantee that your stateful applications will be running in an on-prem environment that you manage, but you might be running these in cloud instances. And in fact, a lot of these technologies are there to enable cloud strategies and cloud technologies. So we expect the cloud-native storage system to be secure and offer services like encryption and integrate with our backend authentication or authorization mechanisms that are native to Kubernetes. A lot of the systems that cloud-native storage needs to work with are going to be just more agile. And I know that's terribly cliched, but what we're saying here is that there will be a lot more moving parts in cloud-native environments. Nodes will come and go, and you will use automatic scaling capabilities with your orchestrator. And your storage environment needs to be able to adapt to that and be agile too in those environments. And the last 2 points kind of tie into that. So in these environments where there are lots of moving parts, where servers are coming and going, and scaling is dynamic, the storage system needs to be able to be performant and offer predictable performance in these distributed environments. And it also needs to maintain availability and redundancy of your data as all of these environments change. So we move on to talk a little bit about the data access interfaces and the orchestrator and management interfaces. And when we talk about data access interfaces, this is basically how an application or a workload is going to be consuming the storage. So in general, and we've defined this in the Cloud Native Storage white paper, is we've kind of got two main buckets for storage. The first one is volumes, and that covers things like block stores and file systems and shared file systems. And we also have another bucket which we've called creatively API, which covers things like object stores and key value stores and databases, because of course they are all valid. They are all valid persistence layers in cloud native storage. Now, it's probably fair to say, though, that the most mature interfaces that work with Kubernetes are obviously the volume type interfaces. So this leads us to this slide, which kind of covers and gives us a little bit of background as to how the different orchestrators talk to the different operating systems. So what we already mentioned that the workloads that the workloads have a channel to the data plane, and this is how they access volumes and they access the information that's being consumed from the storage systems. But the orchestrator does a lot of work in terms of dynamic provisioning and accessing volumes for consumption through a control plane interface. And there are a number of control plane interfaces, which Jared is going to cover in the next slide. But one thing I just wanted to point out here is that some storage systems might have native drivers that or interfaces that talk directly to Kubernetes and the orchestrator. But there are also a huge plethora of tools and projects that also help with the management and various other frameworks, including Rook, of course, which is one of Jared's projects. So with that, I will hand over to Jared, who will talk to you about the control plane interfaces in a bit more detail.
Yeah, so first I wanted to say definitely tell Alex that I'm very impressed that being able to step in last minute and deliver a keynote is not a position I personally would want to be put into, but it's absolutely seamless. So Alex is a great speaker, and so far 100% of the talks today have been given by Alex, and so now we'll transition into someone else speaking. So I'll try to live up to the bar that you've set already, Alex. And also, I think Lisa does an amazing job of getting this event organized and set up. And if there's anything that I want done correctly in my life, I will come to Lisa to do it. I don't even care what it is. I just ask Lisa to do it. I feel in comfortable hands with Lisa. All right, so let's get back to the topic here. So Alex was just showing you about data plane interfaces and control plane interfaces. So we're going to move out of some of the theory and get into some more of the tactical, practical aspects right now. So some examples here are on this slide for particular control plane interfaces. And the first one on the slide here is about the Kubernetes native drivers. So these are the volume plugins and drivers that allow external storage systems to interface in and integrate in with Kubernetes, provide volumes and storage services to your pods. But they are actually part of the Kubernetes core system. The source code lives within the Kubernetes repo. It's part of the build and packaging and publishing and release process of Kubernetes. So, the big downfall to that is that you were tied to the release of Kubernetes. If you want to make an update to your in-tree volume plugin, you have to wait until the next update of Kubernetes itself. You can't just, willy-nilly put out a patch on some random weekday. Kubernetes has a really, really good release schedule. They stick to it quarterly, so it's not like it's that long of a wait, but you don't have any control over it. The examples of native Kubernetes drivers that are in the source tree of Kubernetes are pretty much all the big ones. Like the cloud provider ones, like Google Persistent Disk and Amazon EBS. Their drivers are inside the source tree and part of the core Kubernetes source code. The next example we have is for Docker. So Docker, as a container runtime, has a particular interface to be able to take an external storage system and provide its storage services as volumes to containers that are running via Docker. And so we'll get into the little more details of that in a couple minutes. But so the Kubernetes Flex Volume, that was Chakri from Diamanti wrote this, and he did a great job of it. But that was an attempt to solve the issue of having to put your storage volume plugins into the Kubernetes source tree. With the Flex Volume, you could then write your own source code outside of Kubernetes. You could ship it and release it according to your own schedule, but you'd still get all the same functionality of being able to dynamically provide volumes from your storage solution to pods in Kubernetes. But that was a kind of an initial early implementation for out-of-tree volume support in Kubernetes. And so what we're seeing everyone moving to now is the container storage interface, which will have a whole panel on it with some of the authors, designers, and contributors to CSI. So obviously those are the experts, and they'll give you all the details. But just real quick is that it is a common storage interface for any container orchestrator to be able to integrate with your storage solution. So you write a single plugin, and that would work with Mesos, Cloud Foundry, Docker Swarm, and Kubernetes as well. So it's really nice to be able to get that flexibility by writing just a single plugin for your storage solution. So let's talk real quick about how Docker itself manages storage and the persistence of data. So if we take a step back and look at what containers are, a container image is basically it's composed of a set of layer of image data of your image layers. So when you're building a container, you start with, I want to start with the Ubuntu image, and then I'm going to add this binary, and I'm going to do this command, and I'm going to download this, and I'm going to put that in the image, so that you have this container image that's full of the custom data that you want it to. But the key here is that it is a set of layers built on top of each other, and those layers are immutable. So what's interesting here is that when you run a container, like when a Docker run, let's say, it brings up a container, it loads your image up with all those image layers stacked on top of each other. But then if your container itself wants to write data, if it wants to persist data, it gets a special layer on top. It's called the container layer. And so this layer, when you're writing it, Any data that your container has there will get written to this container layer, but the downside here is that when the container goes away, that container layer where things were written to is completely ephemeral. It's transient. It's not permanent. The data that you wrote there is gone. So that kind of reinforces the fact that the container images are immutable. Anything that gets written to them will not change that container image. It stays exactly the same, so that when it starts up as a new container, it's the same thing. It's consistent. We know exactly what data to expect in there, which is definitely one of the beauties of containers. So Docker goes about this by a couple different ways. One is a named volume in Docker. And so what this does is that when your container is running on a host machine, you can actually kind of be able to store or write data onto the host machine's file system that your container is running on. And so you can see under here, it's under varlib docker volumes, and all that data that your container is writing to that specific volume will stay persisted on the host. If your container goes away and comes back up again and reuses the same volume, all that data is still there, which is good for persistence, but that obviously has a downfall real quick that we see here, is that this is only on one host. If your container moves to another host, you don't have access to that same data because it was only stored locally on that one host. So here's a couple example commands of what it looks like to use a Docker volume, where you can use a Docker command to create the volume, and then we're running a Docker container which is mounting that volume, doing some writing to it. We have the --rm as well for the container, so when it goes away, the container is deleted, but we show that the volume information, the data on the volume, is still there. So Docker also has the concept of volume plugin, which is the means of Docker to be able to use a plugin to interface with an external storage system, like StorageOS or Ceph or whatever it may be. Where what we gain here is that your container, it will be persisting data to to a volume through a plugin. But then this gives us, instead of just saving it on the host node, this actually saves it to the underlying distributed storage system that is across multiple nodes. So if your container is torn down and started up somewhere else, you will have access to that same data because it's persisted by the entire storage cluster. It's not just on one node, it's on many nodes in the cluster. And we have another example there where we're using a volume. We're specifying to use the StorageOS volume driver so that the backing data won't just be saved to the particular host or node that the container is running on. It's going to actually write it to the StorageOS cluster underneath it. All right, so that's Docker, but let's take a look now at Kubernetes and one of the models there. So I think that there's some really good design principles in Kubernetes that enabled some great scenarios one of them we're going to go through here. So earlier on in Kubernetes, before 1.6, the means that you had to enable your pods to store their storage in an external storage system was through static provisioning. So you'd have an administrator, they'd go and they'd have to manually create these persistent volumes that basically captured volumes that are modeled and captured volumes that are stored in an external distributed storage system. And so the administrator creates this entire pool of them, and so we've got 4 little persistent volumes ready to go. Now the developer or user comes by and they need a volume, so they'll claim one of those volumes. And so notice that it's coming out of this pool that the administrator has statically provisioned, manually gone and created these volumes for us. So the developer has claimed one of those. It's they have access to it, but the problem here we run into real quickly is that we only have 4 of these statically provisioned volumes, right? If we have 4 developers or 4 pods come by and each want a volume, we're out of volumes now. The administrator would have to step in and manually create more, and we can do better than that. So I'm pretty sure it was Kubernetes 1.6, but that introduced the concept of what we call dynamic provisioning, and that made storage management and flexibility and availability, et cetera, of providing storage to our pods so much more smooth. I don't even want to go and think back to before dynamic provisioning. But basically the concept here is that instead of creating specific manual volumes, what the administrator is going to do is create these things called storage classes, which are more, you can think of them as a blueprint for when a pod needs storage. This is the blueprint that you should use to, on demand, dynamically create that storage and make it available for the pod. So we have here as an example that the administrator has created 2 different storage classes, one that kind of captures or models fast storage, maybe that's on SSDs only, and then a standard storage class, which maybe would be on spinning platter disks. So what happens here is that the developer comes along, and they have a claim for, I want to get some storage, please. And so it's not, notice it's not pointing directly at a specific volume that's already been created. It's pointing at the storage class. And so Kubernetes uses the storage class, that blueprint, to go ahead and create on demand a brand new volume that is, in line with or according to the definition for fast storage, and that becomes available for the pod. And so we can do this over and over and over again until we literally run out of underlying physical storage space. We don't have to ask the administrator, oh, we ran out of the 4 volumes, can you create a 5th one for me? They'll just be created on demand until we run out of space in our terabyte plus cluster. So this is an example of what a storage class actually looks like. Now, this enforces the separation of concerns approach here, where the administrator, they're the ones that have to know about these details of, okay, the standard storage class in my cluster as an administrator is going to use the acme.com storage provisioner. So that's the type of storage that's going to be the backing underlying storage cluster. It's going to use this particular type of disks, SSDs only. It's going to have a certain quality of service of 500 IOPS. And it's going to have a policy of retaining the data. So when the pod is done, don't delete the data, please retain it. And so this is using having knowledge of specific information in the cluster of what provisioners or what storage clusters are actually installed there. So the administrator is responsible for this. And through a separation of concerns, the persistent volume claim is what an end user would see. So the user doesn't know anything about the details of this cluster, right? They're not an administrator. Their application, their pod that they want to create doesn't know anything about the underlying storage either. So what they get is an abstracted view of what type of storage they want. So what they need to know is, how do they want to access it? Do they want to have multiple writers? Do they want to have only a single reader-writer exclusive usage of the storage? And how much storage do they want? This particular user here wants 100 gigs, so that's where they're going to get provisioned. And now notice that it's pointing to the storage class. So that blueprint that the administrator set up is what this particular user is asking for. Give me the standard storage. I don't need fast storage. Just give me standard. And they don't have to know where it's coming from or any details about it. Cool, so that's how the basic overflow or user experience of storage works in Kubernetes. And so the special interest group for storage, SIG Storage in Kubernetes, has a really good team of contributors and folks that have done some amazing work in Kubernetes. And so we just wanted to talk about what are some of the new features in storage of Kubernetes that that are recent and you may not have been exposed to yet. So there's a number of them here because SIG Storage is always a busy group. But one thing that's pretty cool is that volume snapshots are being incorporated into the Kubernetes API. So there'll be a standard way to whatever your underlying storage system is underneath to be able to create a snapshot for disaster recovery purposes and back it up off-site, et cetera. So that'll be a standard do it from kube control on the command line way to do that. Local persistent volumes is cool because some storage systems want to be able to use the raw devices or be able to have access to host resources. And that's been a pretty clunky way to do that, of managing each storage system having to manage that state themselves, of claiming each disk, hope they're not stomping on each other, of one storage system wanting the disk and another one wanting it also. And now this is built into Kubernetes to have that automatic management and lifecycle orchestration of local disks that's built into Kubernetes now. Mount propagation is interesting because you can take 2 containers, and before their bind mounts to the local host file system was completely private. So one container would mount the file system of the host, another one would mount something on the file system too, and they wouldn't be able to see each other. But now you can propagate that mount from one container to another so they can share data across 2 different containers, 2 different pods even. Raw block volumes are good because most of the time with an external volume plugin, what you get is a file system. You get a volume provision for you, but it also has a file system like ext4 or better fast, whatever it may be. But now instead you can be handed the raw volume. If you know how to speak, if your application knows how to speak to a raw block device, then you can, for performance reasons, be able to use that without having to go through a file system anymore. Topology-aware scheduling is really good because before this was invented, you could run into a situation where you get a pod scheduled in one zone of your cluster, but the block is provisioned, the device, the volume is provisioned in another part of your cluster, and they can't speak to each other. So that pod is actually entirely unschedulable. So now when the pods are being scheduled, the scheduler can take into account where is the volume going to live, what is the topology of the cluster, and make smart decisions about making sure those 2 can talk to each other. And then one of the most recent features is volume resizing. So I think this is part of the CSI spec, But as on the Rook project, we get asked this a lot. Of somebody, maybe they created a 100 gig volume and their pod's using up all those 100 gigs. They might want to expand it. They might want to make it a 200 gig volume. And so being able to dynamically resize a provisioned volume so you don't have to guess up front how much space your pod is going to use for your volume, you can just change it over time online while the pod is using it. Cool, so that's the end of here, and I don't know what the schedule is here, but I think we probably have some time for questions. Oh God, that is not what, how long has that been like that for? Okay, cool. Okay, well, does anybody have questions about the static on the screen? Yes, I'm done this soon. Oh, yeah. Oh, it's Luis. I can hear you from up here, I bet.
I just wanted to point out that in the Kubernetes community, we have a features that just brought out on the last slide. Well, we have made it so that most of those features are CSI only. So just want to make sure we clear that, because the in-tree drivers are deprecating. So any new features are always, we're trying to make it always CSI. Okay.
Yeah, and I think that speaks to, Luis, to the great work that's been done on CSI in Kubernetes, that all these new features and this reliability is all available in CSI. So writing, if you have a storage system, then writing a CSI plugin is the great way to go about and take advantage of all those features. Yes.
So one question. Let's say you have one pod using one volume, running on one node. The node goes down. So it's read-write once, right? So for it to be able to be rescheduled, the storage has to be unmounted on the dead node. Usually that's not the case, at least in my experience. Is this something which depends on the driver, and how do all these companies handle this case? Thank you.
Yeah, I can go ahead and answer that. Yeah, and that's actually a really good point too. That's something that we have run into a problem with in the Rook project. Is that you run into, so if your node goes down and you had a pod attached to a volume there, if you can't communicate with that node, it can be difficult to understand if that pod there is still writing to it. Is it using it? Has it effectively stepped away from it and relinquished it? Is it safe to move that volume to another node for the new pod to use? And so some storage systems can handle that. They can be able to, lock out or evict a particular consumer of a virtual volume within the storage cluster. But I think it kind of is storage vendor dependent of what the underlying storage is and how well can they tolerate that situation.
Yeah, just echoing that. I think the failover capability is something that will tend to be storage system or service provider dependent. So if you're using storage from a cloud provider, they might need to detach and reattach, and that process might have a delay, or it might be quick depending on the cloud provider. And similarly, different storage providers have different functionality and different strategies in the way they deal with that. So that's actually a really good question to ask some of the sponsors at the back tables later on.
Can I answer that?
Sure.
I'd like to answer that.
Why don't you come up?
Yeah, join us, Luis.
I would like to answer that because that's a great question, and what we have found is that a lot of cloud vendors, one big cloud vendor starts with an A, and anyway, has that issue. Whoa, that's quite loud. What we have found is that you have to understand how storage systems are designed, right? A storage system is designed for a certain use case. And this is something Alex and I talked about way back when we did a panel back in London. But when you design it for a certain use case, normally those attaching and retaching are done for virtual machines. And the attaching and retaching of a volume is an event that is not done very frequently, right? On a VM use case. But on a container use case, the the environment changes. So you have to understand that you may still use other storage systems that were designed for that model, but the new container model of moving and being evicted from node to node and from zone to zone and region to region, you need a storage system that understands that model and is able to use it accordingly. Okay? Sorry to
Yeah, so just again, right, echoing on that point, we have lots of different options in different storage systems. But one of the things that we do need to consider, and it's like that first principle of cloud native storage, is that we want storage to be application centric. So you want your storage to be able to deal with presenting storage and consuming storage to the actual pods and not to the VMs or the nodes. And that's the point I was referring to in that principle. Otherwise, as your nodes, as your pods and your applications that can be rescheduled across different nodes in a system move around, you need to make sure that the data can actually follow those systems. And I think we have. Do we have any more time?
I think we can save the rest of the questions until the end. So can we give Alex and Jared a nice round of